Hi dear students, in the previous class we were discussing about valence bond theory. Valence bond theory states that a chemical bond is formed by overlapping of atomic orbitals. Instead of saying an electrons are shared and a chemical bond is formed, and the atomic orbitals are a wave function which represents a three-dimensional region where the probability of finding electron is very high. So, as per the valence bond theory, we have discussed about the postulates, we have discussed about what are the factors which will increase the strength of the bond, what are the conditions for an atomic orbital in order to involve in a chemical bonding, and what are the type of overlapping that could be expected depending on the type of atomic orbitals involved in chemical bonding, and what are the mode of overlapping that may happen in order to form a chemical bond. So today we will take an example, that is oxygen molecule and nitrogen molecule. In order to be familiar with the sigma bond and pi bond, we will try to draw the orbital overlapping diagram for oxygen molecule. So as we have taken in case of hydrogen molecule, we will take oxygen molecule, and the oxygen molecule is formed by a combination of OA and OB, two ions. And if you recall the Lewis dot structure, the bonding in oxygen molecule is like this. O double bond O, like this. Two lone pairs, two bond pairs, and two lone pairs. So 2 plus 2, 4 plus 4, 8. This oxygen is happy and this oxygen is happy. That means there are two bonds between two oxygen atoms in an oxygen molecule. So one will be always sigma bond. The first bond will be always sigma, and the second bond will be pi bond. That's how it will be. So when you draw the orbital overlapping diagram, you need to show that how the sigma bond is formed and how the pi bond is formed. And the very initial step before drawing the orbital overlapping diagram of oxygen molecule is you need to write down the electronic configuration. So oxygen electronic configuration is 1s2, 2s2, 2p4. Of course, the atomic number of oxygen is 8. So electronic configuration is 1s2, 2s2, 2p4. And when we were discussing about the postulates of valence bond theory, the valence orbitals having an unpaired electron with opposite spin will go for overlapping. So you have to take the outermost shell, outermost subshell, and draw the box diagram. So outermost subshell for OA, it is there are 3 p orbitals. Of course, this p, if you take this 2p, this 2 is the number of shell, and this p represents the subshell. The quantum number, if you take, it is the azimuthal quantum number 1. So p is the labeling for azimuthal quantum number 1, and this 4 represents the number of electrons. So p subshell is having 3 orbitals, because for p subshell L value is equal to 1. For a particular L value, the possible m values are 0 to, if it is p subshell, how many orbitals are there in p subshell? How do you find out? 2l plus 1, right? So 2 into 1 plus 1, 3 orbitals will be there. So we can draw 3 p orbitals. And if you take the number of electrons, there are 4 electrons. According to Hund's rule of maximum multiplicity, no pairing of electrons happens until each degenerate orbital is singly occupied. So these 3 orbitals are having same n value, that is 2, and same L value. So you know that the orbitals are arranged in the increasing order of their energy. So how do you find out the energy of an orbital if you ask? n plus L rule. If the n plus L value is identical, they have same energy. So these three orbitals, if you take, they have same n value, same L value. So n is 2, L is 1. So 1 plus 2 is equal to 3. So for all the three orbitals, the n plus L value is 3. So they are called degenerate orbitals. So these orbitals are called degenerate orbitals. So in degenerate orbitals, the pairing of electron happens until each orbital is singly occupied. So here there are 4 electrons. Each orbital will be singly occupied. So we have distributed 3 electrons and the 4th electron will be coming over here. So you have 2 orbitals having unpaired electron. So the valency of oxygen is 2. 2 is the valency of oxygen. So if you take the oxygen molecule, this is how the structure, the Lewis structure. So whenever there is a double bond between 2 atoms of a molecule, the first bond will be always sigma and the second bond will be pi. So if you are trying to draw the the orbital overlapping diagram for oxygen, we know that there are 2 p orbitals from each oxygen atom. This 2 p orbital will be perpendicular to each other, 90 degree to each other. So it will be coming like this, one of the orbital, and the second orbital will be like this. And so this is head to head overlapping. So there is a sigma bond, first sigma bond, a sigma bond is formed by head to head overlapping. So they overlap. And this second p orbitals, because if you take a p orbital, they could be like this. So this is how it will be. So you must be remembering that there are 3 p orbitals. One p orbital, if you take it along the z axis, this could be z axis, x axis, y axis. I have taken only 2 p orbitals over here. So please understand, when one p orbital is already overlapped, the other p orbital will be like this. So they cannot go for head to head overlapping. No way they can go for head to head overlapping. So what will happen if you take this case itself? So this is the bond already formed. So it could be like this. See. So this p orbital is backside. So you can take here this p, and this p orbital is there as it is. So here also you can see a p orbital. So only what they can do, they can see face to face. They cannot go for head to head overlapping. That's an issue related to the geometry of the p orbital. So what happens is, this p orbital, the second p orbital which is having an unpaired electron, they can only go for sideways overlapping. Sideways overlapping will be represented like this. So this is upper lobe and this is lower lobe. It doesn't mean 2 bonds are formed. This is a single p orbital and this is another single p orbital. Both of them overlap. You cannot show that overlapping like this. So what do? You draw 2 lines. Upper lobe, 1 line, lower lobe, 1 line. So there is the formation of a single bond. That's it. So there is a sigma bond over here. 2 electrons are paired, and here also there are 2 electrons paired. A sigma bond here and a pi bond over here. Hope you understood. And once the pi bond is formed, you can draw the orbitals like this. So a sigma bond, sigma. Then once the pi bond is formed, it will be like this. Once they overlap. So 2 p orbital, they overlap and they form. This is along the nuclear axis, a line, an imaginary line like this. A egg-like structure on the upper side of the axis and an egg-like structure on the bottom side of the axis. This is how it will be, and you can see that PP overlapping. It will be like this. It's not something like there is a solid something. It's a region where the probability of finding electron is high. Which electrons? Those electrons are involved in pi bonding. That's it. This is a region. This is not electron. This is a region where the pi bonded electrons could be seen. That's it. So this is how it will be. This is what the diagram, orbital overlapping diagram for nitrogen molecule. Sorry, oxygen molecule. So if you take the nitrogen molecule, so nitrogen is having the electronic configuration same way, N2. From the Lewis structure, you know that nitrogen is having 3 bonds. 3 bonds. So if you take first nitrogen atom, electronic on the Z atomic number is 7 and 1s2, 2s2, 2p3. This is what the electronic configuration. And if you take the outermost subshell, that is p subshell, and if you distribute the electrons 1, 2, 3, there are p orbitals having an unpaired electron. 3 orbitals having unpaired electron. So all the 3 can go for overlapping. This is 1, and this is 1. So there are 3 p orbitals and 3 p orbitals of the same subshell. So imagine I have a set model where only 2 p orbitals are there. So the other p orbital is supposed to come over here. So just like, so if you compare with the oxygen molecule, here we have one more extra. What is that? When these 2 p orbitals, so other p orbitals also overlap, there will be a p orbital like this, ready to go for face-to-face overlapping, and there will be a p orbital over here that is also ready to go. This is what to say, in this way, in this axis, the other one is in this axis, vertically, the other one is horizontal. So both of them can go for sideways overlapping. So let's draw the other one over here. So I don't want to draw again, so I will just simplifying it. So if you take nitrogen, there are 3 p orbitals. Already we have drawn one, second one, and the third one will be drawn like this. I give a shade for this because this is the third p orbital. Here also it comes like that. In the same mode, we draw. So there are 3 bonds. One is sigma, 2 pi bond. 1 pi bond already there, and the next pi bond will be formed between these 2 p orbitals. So this is the second pi bond. This is how we will draw the orbital overlapping diagram for nitrogen. So there is a sigma bond and 2 pi bonds. So lateral overlapping. So hope you got a better understanding about the sigma bond and pi bond. Please understand, if there are more than one bond between 2 atoms of a molecule, first bond will be sigma bond and the second bond will be pi bond. Even third also will be pi bond. Only one would be sigma bond because head-to-head overlapping will be permitted by geometry only once. The rest will be face-to-face or lateral overlapping. And this, if you take all the molecule, like we have taken the HF molecule, hydrogen fluoride, but it's simple. If you take polyatomic molecules, it's not 2, more than 2. Multi-atomic molecules, different atoms involved and more than 2 atoms are there in the molecule. More than 2, not more than 2, more than 1 atoms are there in the molecule. So many atoms are involved in the molecule and minimum 2 types of atoms are there in the molecule. We'll take such an example and see how to draw the orbital overlapping diagram. And Best example is CH4. We call it as methane. If you take organic chemistry, if you ask me who is the father of all the molecules in organic chemistry, it's nothing but methane. Now, if you ask me another question, who is the infant of organic chemistry or all the vital compounds, because we are made out of organic molecules. So, if you ask me who is the kid, then also I will say methane. From methane only, we create all other organic molecules. Let it be a drug, let it be anything, because this is the starting point. Or if you ask me, so you can decide whether it is the egg or the hen. Anyway, CH4 is a very important molecule. So if you take CH4 molecule, when you go for orbital overlapping diagram, the strategy is this. Initially, you have to draw the simplified Louis dot structure of CH4. So the simplified Louis dot structure of CH4, if you ask, it's like this. A carbon atom which is surrounded by 4 hydrogen atom by means of a single bond. So what are the observations you can make in this molecule? So the very first observation is this carbon is tetravalent. Tetravalent means the valency of carbon atom it is 4. And the second point it is there are 4 CH bonds. 4 CH bonds. They are not just merely bonds, they are 4 equivalent CH bonds. 4 CH bonds are equivalent. They are equivalent. And one more point it is, from the BSc-PR theory, we have understood that CH4 is a molecule having regular tetrahedral geometry. Tetrahedral geometry. And the angle between two adjacent CH bonds is 109 degree 28 minutes. So this 3, or let us take it 109 degree 28 minutes. There are 4 points now. 3, 4. You have 4 points now. This is carbon is tetravalency of carbon. First point. Second point, 4 CH bonds, and if you take the CH bonds, all of them are equivalent. If you take the third point, this is regular tetrahedral the geometry, and 109 degree 28 minutes is the bond angle between any 2 adjacent CH bonds. So all this points should be approved when you draw the orbital overlapping diagram. So if you take the steps, the very first step it is you have to know the atomic number. Carbon atomic number is 6. Electronic configuration 1s2, 2s2, 2p2. And if you draw the box diagram, it comes like this. So, if you draw the electronic configuration of carbon 1s2, 2s2, 2p2 and the box diagram, it says, according to valence bond theory, the valency means number of atomic orbitals having unpaired electron. So, here you could see only 2 orbitals, 2p orbital having unpaired electron. So, the valency is 2. It is divalent or bivalent. The very first problem you are going to encounter is carbon is tetravalent, but here it is divalent. So how could it be solved? So for that, when it goes for bonding, it is a big business where huge profit will be happening. So you have to contribute a little. What is that contribution is? You have to make the carbon atom excited. So it could be better represented by this electronic configuration. You can show the energy level diagram. So this is ground state, orbital, 2p, 2s. If you take excited state, this is 2s and this is 2p. So when you take, this is different and this is different. Initially it was like this, 2s is having 2 electron and here is having 1 electron and 1 electron. What happens is, in the excitement of forming a bond, the carbon atom will get excited. Excited means one of the electron in 2s orbital will get promoted to 2p orbital. So it will be like this. So after the excitation it will be like this. So see how many orbitals are there having singly occupied atomic orbitals. 1, 2, 3, 4. So it is tetrahedral. That problem is already solved. Now it's better when you draw the orbital overlapping diagram. You have to mention about hydrogen also. There are 4 hydrogen atoms. Atomic number is 1. Electronic configuration is 1s1. So only one orbital of opposite spin. Let it be. We'll come back to that. So it looks easy because there are 4 hydrogen atoms, 1, 2, 3, 4, having an unpaired electron, 1s1. It will be like this orbital. And now here there are 4 orbitals, 1s orbital, 3p orbital. If you draw in a simple way, orbital overlapping. So this is 1p orbital, another p orbital, another p orbital. 3p orbitals. You imagine the same way, like how it is this x, y, and z. That's how it will be. And s orbital will be at the middle. One s orbital, 3p orbital. Now, if you go for overlapping, so one of the hydrogen can overlap here, another hydrogen here, another hydrogen here, and the bond will be 90 degree. And if you take the last hydrogen, it will be taking a pradakshina. It doesn't know where to join because it can join anywhere because SS overlapping now. So the problem is 4 CH bonds cannot be equivalent if it is SS overlapping and SP overlapping. This is S orbital for hydrogen, these 2 SS, and this is SP. There will be different bonds. They will have different strength. Problem number 1. And problem number 2, that cannot have regular geometry, regular tetrahedral geometry, because these 3 bonds will be 90 degree, 4 to nobody knows, it could be somewhere in between 0 to 180 degree. And 109 degree, 28 minute will be only a dream, cannot be reality. So there is something wrong. How could we solve the issue? That's why the new concept, it's been introduced by Linus Pauling. So according to Linus Pauling, this 4 atomic orbitals will go for hybridization. Hybridization. So now the question is, what is hybridization? If you are supposed to paint this entire room by giving a single color and you need 2 liters of paint and you are provided with 4 paints having different color of 500 ml. So what will you do if you wanted to paint the entire room by using with a single color? The outcome must be single in color. You are provided with 4 different colors. How will you manage? Immediately you will tell me, sir, mix it. Mix it. You have to mix. And this mixing is what we call hybridize. So, hybridization is the intermixing of atomic orbitals having similar energy, not identical energy. Similar, slight differences there, even though I have represented like this. Having similar energy and different shape, S orbital, P orbital is having different shape. In order to produce
same number of hybrid orbitals. Once they are intermixed, they cannot be pure atomic orbital, they will be hybrid orbitals. Same number of hybrid orbitals having identical shape and identical energy. This process is called hybridization. So what is hybridization? Hybridization is the intermixing of atomic orbitals having different shape and similar energy in order to form same number of hybrid orbitals having identical shape and identical energy. That's how it will be. Okay, so if you take this, so this is how you have to draw, then you can mention, I'll tell you, this hybridization, there is a close connection between the number of pairs of electrons and hybridization. So here 4 atomic orbitals are hybridized. So same number of hybrid orbitals will be formed. So if you pictorially represent raising this, hope you have written down your notebook. So we have 1 s orbital and 3 p orbital. One is in x-axis, then another one in y-axis, another one in z-axis. So all together will be mixed. So you get hybrid orbitals having identical shape, and each hybrid orbital, it doesn't matter whichever be the hybridization, will be like this. So p orbital, 2 lobes on identical size. This is 2 lobes even for hybrid orbital. One will be a big lobe, another one will be a small lobe. That's how it will be. So 4 hybrid orbitals. And what's the hybrid orbitals? If you talk about that, this hybrid orbital will be geometrically oriented. If there are 4 hybrid orbitals, you recall what you have learned in VSEPR theory. If there are 4 pairs of electron, each pair of electron will be directed towards the corners of regular tetrahedron. This hybrid orbitals also will be directed towards the corners of regular tetrahedron. This is how it will be. So 4 hybrid orbitals directed towards the corners of regular tetrahedron. That's how this will be. This is the base, this is the apex. So 4 hybrid orbitals having the shape of regular tetrahedron will be formed, and this process is called hybridization. Why did we go for hybridization? If you wanted to satisfy the primary observation that we made from the Louis dot structure and VSEPR theory, and we wanted to update the concept according to atomic orbital quantum mechanical concept, and these observation cannot be wrong. You need to explain it by taking the quantum mechanical concept. That's why we have gone for hybridization. So once it is hybridized, see, you have 4 equivalent bonds, 4 equivalent orbitals. Each one will be sp3 hybrid orbital. This is an sp3 hybrid orbital, this is another sp3, this is another sp3, this is another sp3. So you got 4 sp3 hybrid orbitals, and 4 of them are equivalent. Now they can overlap with the hydrogen atoms s orbital, equivalent bonds. And this is having a regular geometry, that is tetrahedral, and of course the angle will be 109 degree 28 minute. This is how it is going to come. Please see. 4 hybrid orbitals, bond angle will be 109 degree 28 minute, and this is 1 sp3, this is 1 sp3, this is 1 sp3, this is 1 sp3. Please understand that p3 is not the number of electron, it is the number of p orbitals involved. So 3 p orbitals and 1 s orbital, totally 4 hybrid orbitals. Okay, and there is a close connection between the number of pairs of electron and hybridization. This is how it will be. Suppose when you are counting the number of pairs of electron, please understand, if it is a double bond or a single bond or a triple bond, it will be counted as a single one. If there are two atoms connected by single bond or double bond or triple bond, it doesn't matter, it will be counted as single pair. Lone pair will be separately counted. So you should count totally how many pairs of electron. It doesn't matter it is bond pair or lone pair. So that many hybrid orbitals are required. So if there are two hybrid orbitals, the hybridization will be from 1s and 1p for two pairs of electron. If it is three pairs of electron, you cannot increase s, it will be sp2. If there is four pairs of electron, it will be sp3, the current example. If there are five pairs of electron, sp3, p orbital is only 3, it cannot be 4. Then you will borrow from d. So 5, sp3, d2 is for 6. We have seen an example SF6. This is for PCl5, 5 pairs of electron. So please keep in your mind, count how many pairs of electrons are there around the central atom. That many hybrid orbitals are required. So here 4, so sp3. So once you actually draw the electronic configuration, you can just state there are the Louis dot structure of CH4 molecule is like this. You would have drawn all this on the right side and you can accumulate this information. This is not required actually for the exam, so that you will correlate both. Okay, so you can directly state the sp3 hybridization from where, by looking at this 4 bonds are there. Just take sp3 hybridization and draw this, and you can next, once you draw this, next you can draw actually you will be thinking why I have drawn a small, because actually the hybrid orbital will have a big lobe and a small lobe. The small lobe need not show actually, it's actually there will be a small lobe. So plus there are 4 s orbitals, 1, 2, 3, 4, and it will give like this. 4 hybrid orbitals, 3 hybrid orbitals, 1 s orbital of hydrogen, another s orbital of hydrogen, s orbital of hydrogen, like this. So 4 sigma bonds having 4 CH equivalent bonds. The geometry is tetrahedron, angle is 109 degree, 28 minutes. You could understand from this is how it will be. See, tetrahedron, bond angle. This is sigma bond, CH sigma bond, CH sigma bond. This is how it will be. Tetrahedron. Hope you understood. This is what we call sp3 hybridization. We'll discuss.